Hello students, welcome to EPG Pathshala. I am Professor P03 from the University of Jammu. Today we are going to discuss about a module entitled Application of X-ray Diffraction in the Study of Crystal Defects Part 1 under the paper Crystallography and Crystal Growth. Now let us see what we learn from this module. It is to learn about application of X-ray diffraction in the delineation of various types of imperfections in crystals. Grain boundaries are the defects that can be detected and characterized by the X-ray Lavie method using a fine focus. Dislocations are detected and characterized by employing X-ray topographic techniques. Scanning of crystals by X-ray topographic method detect defects like impurity aggregates, inclusions, process-induced defects, other defects that originate from growth faults, namely striations, growth facets, growth bands, bubbles, skeletal crystals, microcrystals embedded in the crystal body. It is explained that X-ray topographic techniques is a bulk method of directly observing defects in a crystal. Basic principles of X-ray diffraction topography are explained. Contrast produced in X-ray diffraction by imperfect regions of the crystal for both Bragg as well as Lavie cases leading to extinction contrast is explained. Application of X-ray diffraction in the study of crystal defects. We have already studied the application and effectiveness of X-ray diffraction as applied to exploration of the internal structure of crystals. The diffraction techniques help us to determine the lattice parameters of crystals. In order to make complete crystallographic characterization, one has to know about the internal structure, which includes the exact position of atoms, ions, or molecules in the unit cell. To be able to do that, one is required to have accurate measurement of intensities of a very large number of Bragg reflections. Analysis of crystal structure is quite a specialized topic to be dealt with, and those interested may consult references given at the relevant places. The techniques as applied to this aspect of X-ray crystallography is undergoing very rapid changes, both in terms of accuracy of measurements of intensities, automation, and automatic computation. Crystallographic measurements are no longer dependent on a computer-controlled diffractometer. The analysis of diffraction data, no matter how long and elaborate, is done through computer-controlled automation. It may, however, be noted that real crystals are not perfect, and one is required to assess the crystal perfection. So far as determination of lattice parameters of crystals is concerned, it is not influenced much by the imperfections present in the sample. It, however, does depend on the type of imperfection. There are imperfections like vacancies, which, if present in limited concentration, may not have any significant effect on measurement of lattice parameters. However, it is a fact that detection, observation, assessment, extent and type of defect in a given crystal is extremely important. Automated diffractometers, software programs, and control over radiation are being continuously modified and advanced to bring about accuracy and rapidity in the solution and refinement of data recording. X-ray diffraction does provide a powerful probe for investigating defects in crystals, and this is what we shall describe in this unit. Most of the properties of crystals are structure sensitive. Imperfections, if any, can affect their properties. Evaluation of imperfections in crystals is therefore important. X-ray diffraction is one of the probes which can be used effectively for assessment of perfection in crystals. X-ray diffraction techniques will be discussed here as applied to direct observation, detection, and assessment of defects in crystals. Let us talk about X-ray topographic technique. Imperfections in crystals include point defects like vacancies and impurities. Second, one-dimensional defects like dislocations. Thirdly, two-dimensional grain boundaries, low-angle tilt boundaries, or sub-grain boundaries, and twin boundaries. Number 4, stacking faults. And 5, three-dimensional defects like bubbles, skeletal crystals, and so on. Dislocations, which are classified as one-dimensional defects, affect the mechanical properties of crystals. Grain boundaries are the boundaries which separate the two grains that are crystallographically misoriented with respect to each other by a very small angle of not exceeding 10 degrees. The lattices of the two separate grains are slightly tilted with respect to each other. This type of defect can be detected and characterized by the X-ray Lowey method using a fine focus. X-ray beams which have a divergence of nearly 10 or minus 3 radians. In fact, the dislocation model of low-angle tilt boundary, as suggested by Vogel et al., received confirmation when the angle of tilt between the two grains of germanium as measured from H method and X-ray diffraction matched. The low-angle tilt boundaries are delineated and characterized by using X-ray Lowey method, where a fine focus X-ray source and collimated with very small slits, allowing X-ray beams of divergence of nearly 10 or minus 3 radians. Dislocations are not easily observable by X-ray techniques. However, X-ray diffraction topographic technique can detect them, and it is possible to characterize them also. The other type of defects, like point defects and their aggregates, cannot be made directly observable by using X-ray topographic techniques. Such type of defects, however, can be used by measuring diffuse X-ray scattering from regions of reciprocal space close to a reciprocal lattice point, and one can obtain information concerning point defects and their aggregates. Scanning of crystals by X-ray topographic methods can effectively detect defects like impurity aggregates, inclusions, process-induced defects, and other defects which originate from growth fault like growth facets, striations, growth bands, skeletal crystals, air bubbles, microcrystals within the body of bulk crystal, etc. X-ray topographic techniques is a bulk method of directly observing defects in crystals. The basic principles of X-ray topography. X-ray topographic technique is based on the fact that intensity of X-ray beam, which is diffracted by a perfect region within a crystal, is different from the one diffracted by an imperfect region in the crystal. Let us consider diffraction of a divergent beam of white X-rays from a perfect and an imperfect region of a crystal and compare the two processes. To explain this, we consider the following two different cases. A. Diffraction of divergent beam of white X-rays from perfect regions of the crystal as shown in figure 9.1. B. Diffraction of divergent beam of white X-rays from deformed that is imperfect regions of the crystal as illustrated in figure 9.2. In figures 9.1 and 9.2, we have a fairly divergent beam of white X-rays which is used to explore the crystal. When the crystal is set so as to have its perfect region exposed to X radiation, the perfect region of the crystal will choose those rays out of the divergent X-ray beam which satisfies the Bragg law. As such, only a small fraction of the total incident beam of X-rays will get diffracted, as can be ascertained from figure 9.1. However, in the defective area, the diffracting planes are distorted, and the normal drawn at different points in this disturbed area cannot be parallel to each other, but instead would be pointing in different directions in space, as is shown in figure 9.2. Diffraction of X-rays has to follow laws of reflection. Under these conditions, the number of rays which satisfy Bragg's law will be much larger as compared to those in the former case, that is the perfect region. It would simply mean that the intensity of the diffracted X-ray beam from the disturbed or the deformed areas would be much more as compared to diffraction of X-ray beam from the perfect areas or regions of the crystal. It is this variation of the intensity of diffracted X-ray beam which can be a probe for differentiating perfect regions within a crystal from the imperfect regions. So, out of the total beam that is incident and striking a perfect region of the crystal, only a small fraction of it is diffracted. If, however, a divergent wide beam of X-rays strikes the imperfect or deformed region of the crystal, the normal to the lattice points at different points within the deformed regions are not parallel to each other, unlike the one striking a perfect region, and as such would diffract X-rays which lie within a large angular range. It leads to much larger intensity of diffraction X-rays as compared to the one in case of diffracted X-rays from perfect regions of the crystal. The other factor is that the interplanar spacing and so the d values of the lattice planes in the imperfect or deformed regions of the crystal varies from point to point. The incident X-ray beam, being white, involves several wavelengths, because of which different regions select suitable wavelengths which satisfy Bragg's law. This reinforces the intensity of the diffracted beam from imperfect regions. It is because of these factors that deformed or imperfect regions appear dark in the lighter background when the same is recorded on a photograph called as X-ray topography. So one may sum up that the deformed or imperfect region in a crystal pose two problems to the incident beam of X-rays. One being that the normals drawn at every point within the deformed or imperfect region will not be parallel, and second, the interplanar spacing, that is d values, will vary if one goes from point to point. When divergent beam of white X-rays is incident on the perfect regions of the crystal, it will choose some rays out of the divergent beam that satisfies Bragg's law. Consequently, only a small fraction of the total beam gets diffracted, leading to decreased intensity of the diffracted beam as compared to the one diffracted from the imperfect regions of the crystal. In short, the intensity of the diffracted rays from the imperfect regions of the crystal is expected to be much larger than the one diffracted from perfect regions of the crystal. The second difference is on account of varying interplanar spacing at different points in the deformed or imperfect regions of the crystal. Since d value is an important parameter in the Bragg equation, Any variation in it is bound to have some suitable parameters for Bragg equation to be satisfied. Now suppose the incident X-ray beam is well collimated and monochromatic. In this case, the perfect region of the crystal, which will have uniformly carrying the same value of D at every point, will lead to large intensity of the diffracted beam as shown in figure 9.3. However, variation of D value at every point of the deformed region will not allow many X-ray beams to get diffracted, leading to decrease in intensity of the diffracted beam, because of which it will appear white on a dark background when the same is recorded on the photographic film. This we can see in figure 9.4. What has been discussed above pertains to reflection geometry, in which application of Bragg equation plays the shots. The diffracted X-ray beam gets reflected on the same side on which the probing beam is incident. Now let us consider the situation in transmission, popularly known as Lowe case or observation in transmission geometry. When transmission geometry is applied for diffraction from perfect crystals, several other phenomena like anomalous transmission and Pendelow-Sung bridges are called into play. In this mode, there are two types of situations, which are on account of the thickness and the absorption coefficient of the crystal. Let us consider the case when absorption coefficient mu and the thickness T of the crystal are such that mu T is less than 1. Under this situation, the diffracted and the directed beams are treated as independent of each other. In the normal topographic experiments, the probing X-ray beams have a divergence much larger than that of the width of the diffraction curve, as is indicated in figure 9.1 and 9.2. It is obvious, therefore, that the deformation, defects, imperfections appear black on a gray background of the topography. Now suppose that we are dealing with a case when absorption coefficient mu and the thickness small t of the crystal are such that mu t is either greater or equal to 10. In this situation, the diffracted and the direct beam are strongly coupled to each other in the crystal. The dynamical theory suggests that the direct and diffracted beams are strong enough and may be termed as a case of anomalous transmission. To make it happen, the specimen has to be so held that there is diffraction from a set of lattice planes and all of whose atoms scatter in phase. It was experimentally observed by Bormann that it happens in a narrow range of angles. It is popularly known as Bormann effect. The dynamical theory suggests that the direct and diffracted beams should have comparable amplitudes and so result into formation of standing waves between the lattice planes from which diffraction is under consideration. On leaving the crystal surface, the direct, that is forward diffracted, and the diffracted beams separate out. As a result, the residual direct, the forward diffracted beams, and the diffracted beam get recorded at respective places on the photographic film. It means that there are two beams in the direction of the probing X-ray beam as shown in figure 9.5. According to dynamical theory, the nodes of the standing waves on falling on the atomic sites do not get absorbed because of photoelectric emission. As a result, the waves travel without any noticeable attenuation in the crystal, and on reaching the exact surface of the crystal get separated into direct and diffracted beams, making an angle of 2 theta b with each other, as is illustrated in the schematic diagram of figure 9.5. Figure 9.5 shows formation of standing waves between the lattice planes from which the diffraction occurs. Within the crystal, the standing waves travel along the lattice planes, the residual probing X-ray beam making an angle theta b with the direction of propagation of the standing wave. It means that the direct beam on getting diffracted does not coincide with the direction of the probing beam. It may be parallel to it, but they are spatially displaced. In order to fully understand this phenomenon, one is required to go through the dynamical theory, the further details of which may not be discussed here. It is important to know that the standing wave formation can take place only in those regions of the crystal which are perfect. That is not so in case of deformed or imperfect areas, wherein the coupling between the direct and the diffracted beams gets disrupted and breaks down. As a consequence of this, the conditions are not conducive for anomalous transmission, and hence these regions appear to be white on a black background in the photograph. What has been explained above is that if we use a divergent beam of white X-rays and allow it to strike the crystal so as to be diffracted from a perfect region of the crystal, the region will make selection for diffraction of such a group of X-rays whose angle of incidence lies within narrow angular range. Thus, only a small fraction of the total incident beam will get diffracted as depicted in figure 9.1. If, however, it were diffracted of a divergent beam of X-rays from an imperfect deformed region of the crystal, the diffracted intensity would be much larger when compared to that of a case in figure 9.1. The reason being that since the area involved is deformed, the normal to the lattice planes at different points in that deformed region would not be parallel to each other, with the result that the deformed region can diffract X-rays that fall within large angular range as depicted in figure 9.2. If we were to consider diffraction of a well-collimated beam of monochromatic X-ray beam from a perfect region of a crystal, the intensity of the diffracted X-ray beam is a large fraction of that of the incident X-ray beam, as is shown in figure 9.3. The situation would be different if we were to consider diffraction of a well-collimated monochromatic X-ray beam from an imperfect region of the crystal. The diffracted X-ray beam will cover a very small fraction of the incident X-ray beam as described in figure 9.4. It is therefore clear that there is contrast produced in X-ray diffraction by imperfect regions of the crystal as explained above for both Bragg as well as Lowe case, and is in reality what may be called as extinction contrast. It is this contrast which makes imperfect or deformed regions of the crystal observable. The contrast caused by imperfect or deformed regions of the crystal to the diffracted X-ray, both in Bragg geometry as well as in Lowe geometry, is known as extinction contrast. Other than these two modes of causing extinction contrast, there is one more means of causing contrast which is different from what has been described above. Suppose we have a crystal in which a region is crystallographically differently oriented as a whole from the rest of the remaining volume of the crystal. While Bragg's law may not be satisfied by the imperfect or misoriented region, it may well be satisfied by the rest of the crystal, which would eventually result into creation of contrast on the topographs. However, it is a different kind of contrast which may manifest itself in the form of orientation contrast. Crystals showing orientation contrast are the ones which are imperfect. Let us now summarize of what we have discussed so far. In this module, we have discussed application of X-ray diffraction in the delineation of various types of imperfections in crystals. That the presence of grain boundaries can be detected and characterized by the X-ray Lowey method using a fine focus is described. That X-ray diffraction topographic techniques can detect and characterize dislocations in crystals is explained. Impurity aggregates, inclusions, process-induced defects, and imperfections arising as a result of fault in the crystal growth process, namely growth facets, striations, growth bands, skeletal crystals, air bubbles, microcrystals embedded in the bulk crystal, and several others can be effectively detected by scanning of crystals by X-ray topographic techniques. Basic principles of X-ray topography are explained. Contrast produced in X-ray diffraction topographs by imperfect regions of the crystals known as extinction contrast are explained.